Hello and welcome back. Last time we talked about data pre-processing and at the end we even built a basic model, a very basic model, and we evaluated the accuracy of the model. So today I want to spend a little bit of more time talking about model evaluation. If you're building a model, a data science model, you have to be able to measure how good your model is. This is a very important topic, and you have to make sure that you have a good understanding of the different approaches and different metrics for evaluating model performance. You would be surprised how many times I've interviewed candidates for even mid-level or advanced data science positions, and I've seen candidates struggle to explain how they would measure the goodness of their models or explain what different model evaluation metrics mean. If you're a data scientist, you spend a good chunk of your time building models. So if you're building a model, you have to be able to measure how good your model is performing. And so this is an extremely important topic. This might save the day for you in a real data science task that you're working on or maybe in a future interview. So let's get started by kind of talking about a story. So let's say we have a physician friend and patients come to this physician to get a diagnosis. They want to know if they have a particular disease X or they don't have it. So and what we say is we can build a model to automate that process given patients' data or features. We can predict if a patient has or does not have a particular disease. And so our physician friends put together a test data set, and he's gonna use that to measure how good our model is performing. So today we're not focusing on how we're going to build that model. That's the topic of our next videos. Today we're just talking about, given a model, how do we measure the goodness of that model, the performance of that model. So let's say our physician in this story kind of looks at their records, and they put together a sample of 100 patients. This is our test data set. So we have a test data set, and this has 100 patients in it. This is information about 100 patients, and this is historical records. So our physician exactly knows what the confirmed diagnosis was for this patient. So let's say we had 15 patients with disease X, and we have 85 patients without this disease X, and these are confirmed cases. This is the ground truth. And we don't have access to this data set for training purposes because if you remember from our last video, we want to keep our training data and our test data separate. This is going to serve as new data, our test data, to measure how good our model is going to be. This is a binary classification task. So for every case, every patient, every record, we want to make a decision. And that decision is either going to be, yes, this patient has that disease, or no, this patient doesn't have that disease. Or we can call it a positive decision or a negative decision. Positive meaning that the patient has the disease, negative meaning that the patient doesn't have the disease. So if we think about it, in reality, the ground truth is that each patient in our test data set either has the disease or doesn't have the disease. So there is two cases. There is two distinct categories or cases. And then if you think about the predictions that your model is going to make about each patient, you also have two cases. Your model is going to say, yes, the patient has the disease, it's going to make a positive prediction, or it's going to say, no, the patient doesn't have the disease, a negative. So the ground truth reality, we have two cases, and our model predictions for every patient is going to be two cases. So if you think about the combination of what the actual or the ground truth label is and what your model is predicting, the universe of all possible decisions your model can make is going to be four different things. So let's put together a little table to describe this. So, so this is gonna be my what we call ground truth labels. This is confirmed cases. These are historical cases that our physician put together so the physician knows what the reality of the case was. So let's explain these four cases in a table. We know some patients are going to be positive in reality and some patients are negative. This has nothing to do with our predictions. These are confirmed cases. This is the truth. And then when we make predictions, so this is predictions. Our model, our data science model, may predict some of these cases as positive and some other cases as negative. So we're going to have a table with four cases in it. And so when the ground truth is positive and we predict, we make a decision, our model makes a decision and says, yes, this is positive, that's a good decision. So we detected the positive case. And so these are the cases that we're gonna call true positive. It's a good thing. Now, if the label for a case or a patient is negative, which means the patient doesn't have the disease, and when we ask our model, when we show the data about this patient to our model, and our model makes a prediction and says, no, this patient doesn't have the disease, then it's also a good thing because the prediction matches the ground truth label. So this is also a good decision, and we're going to call it true negatives. So these are the two types of good decisions: true positives and true negatives. Two types of good decisions our model is making. And so your challenge in building a model is going to be to push these numbers as high as you can. You really want a high number of true positives and a high number of true negatives. Now your model is also going to make mistakes. For example, if the label for an instance, a patient, is negative, but your model is making a mistake and is predicting it as positive, well, this is a bad decision because this person doesn't have the disease, and your model is telling us that person actually does have the disease. And so this is what we call a false positive. So false positive meaning that the model predicted it to be positive, but in reality it's a false prediction. It's positive by being false. It's the reality of it is that it's a negative label. A second type of error that your model can make is when the ground truth label is positive. This is a confirmed case of the disease, but your model doesn't detect it. So your model comes back and says negative, this patient doesn't have the disease. And so this is a false negative case, meaning that your model is predicting a case to be negative where in fact it's a positive case. And so we are interested in the good decisions, and that would be decisions on the diagonal of kind of this diagonal true positive, true negatives of this table, which by the way we call confusion matrix. This is our confusion matrix. So true positives, true negatives, good decisions, false positives, false negatives, bad decisions. And so every metric that you're gonna compute to measure the goodness of your model is gonna be based on these four numbers. So let's start by just basics, accuracy. So last time when we built a basic model, we measured the accuracy of the model. So what does accuracy mean? Accuracy is number of all decisions. So your model is making a number of decisions, right? In this case, we have 100 patients, and so your model is going to make a prediction for every patient, and so your model is making 100 decisions. And so the question is, how many of these decisions are good decisions? And so the numerator is going to be number of correct or good decisions. Now, when we make predictions and we put together this confusion matrix, let's say this is the numbers that we get. We have 5 true positives, 15 false positives, 10 false negatives, and 70 true negatives. So first of all, let me show you something. If you add up these 4 numbers, you should end up getting the total, which is the total number of patients. So we started by a data set. We were provided a data set of 100 patients, and we made decisions, we made predictions about these patients. And so our total number of decisions should match that number. So basically what we're saying is true positives plus false positives plus false negatives plus true negatives should be 100. And basically 5 plus 15 plus 10 plus 70, this is going to be 100. And so that's where we get the 100, the total number of decisions. And so we made 100 decisions, and each decision, we look at every single decision and we place that decision in one of these 4 boxes: the true positive box, the false positive box, the false negative or true negative box. And basically you take the first prediction, you compare that prediction to the ground truth label, what you know the case happened to be, the reality of the case, and if your prediction and the correct label match, then depending on whether you made a positive prediction or negative prediction, you're going to put it in one of the true positive or true negative boxes or cells. And similarly, if your prediction doesn't match the ground truth label, that means you made a mistake, your model made a mistake. And depending on what the case is, whether the reality was true but you predicted false, or the reality was false but you predicted true, you're going to place that decision in one of the 2 error boxes, the false positive or false negative box. So coming back to computing accuracy, we know we've made 100 decisions, and the question is, how many of these decisions were good decisions? And as you can see, the numbers on the diagonal of this table, the true positives and true negatives, is really kind of good decisions. And so we have basically true positives plus true negatives, which are good decisions. And so we have 5 true positives, we have 70 true negatives. So in total we have 75 good decisions. Out of 100 decisions, we have 75 good decisions. And so our accuracy is 0.75. It's a number between 0 and 1, or if you want to express it in percentage, our accuracy would be 75%. And this is what we last time we computed automatically when we built our model. So okay, so we have a model that's 75% accurate. If you think about it, I could basically build a model that's really not smart. All it's doing is it's just predicting all patients to either have the disease or not have the disease. And so if you look at my confusion matrix of 100 patients, if you look at the 2 numbers under the ground truth column N, that's the total number of negatives, patients who do not have the disease. And as we know, we have 85 patients that do not have the disease. And so you see that number 85 is distributed between 70 and 15. So that's 85. If you have a model that's really not that smart, it's not doing anything, it's just looking at which label has the most patients in it. Is it positive patients or negative patients? So we have 15 positive patients, 85 negative patients. And all your model is doing is it's going to predict everyone in your data set with the same decision. It's if you have a model that basically says no one has the disease, and if you think about it, if you have a model like that, if you have a classifier like that, and if you measure the accuracy of that model, your model is going to be 85% accurate. Now, what does this mean? This is a really bad model. It's not helping you. It's not helping you to detect the disease. And yet, it's 85% accurate. And the reason you get a relatively high accuracy number is because, in this case, it's because your data is imbalanced. Like you have more patients without that disease, and so most of your data set is not going to have that disease, and so your model is basically cheating by saying no one has the disease, and it manages to get a high score. And so that's why, especially if your data set doesn't have, it's not a balanced data set, then it's not enough just to measure the accuracy of the model. You also want to use more sophisticated metrics to more accurately capture how good your model is. The problem is going to be even more severe if you think about some other use cases, like think about fraud detection, right? Of thousands of transactions that happen, usually maybe one or two might be fraudulent, and every other transaction is going to be good. And so if you measure a model that is absolutely not capable of detecting any fraudulent transactions, if you predict every transaction to be good, you will have a model that's maybe 99.99% accurate, and still it's a useless model. And so because of these reasons, it's usually not enough to measure just the accuracy of the model. For more balanced data sets, accuracy gives you a good sense of how your model is performing, and it's a good practice to always report accuracy of that model. It's a basic measure to measure the performance of your model, but it should never be the only measure that you're reporting. You should always complement the accuracy with other more sophisticated metrics. And so a second metric that we're going to use is called recall, that you always have to report with any model that you're building. And so let's think about recall conceptually. There are simple formulas for metrics like recall and other metrics that we are going to look at, like precision and F1. But I think you need to have an intuitive understanding of the metrics, and like I said, all these metrics have expressions in terms of the four quantities in the confusion matrix: the true positive, false negative, and true negative. So if you think about recall, and if you think about your data set, we had 100 patients, right? And 15 of our patients were positive. And so the question is, the reason I built this model is I wanted to be able to automate the process of detecting patients with a particular disease, specifically those 15 patients. And so once your model makes predictions, then the question is going to be, one way to measure the success of your model is to ask the following question: how many of those 15 positive patients, were detected by your model? So if your model is detecting 14 out of the 15 patients, then it's good. But if your model is only predicting correctly one or two of those cases, then probably that's not good. So we want to capture that concept. And so let's put it in words. So again, it's going to be a ratio, and all these metrics end up being a number between 0 and 1. And you can always multiply that number by 100, which is going to give you a percentage. So the denominator is going to be all positive cases. So this is going to be all patients that have the disease, right? So think about the question we asked. Of all the patients, so we're focusing on only patients which are confirmed to be positive to have that disease. So all positive cases is going to be our denominator. The numerator, we're going to have a number of correctly detected or predicted cases, positive cases. So how many of those positives did our model detect? And so if you think about it, all positive cases is going to be, well, our data set had 15 positive cases. And you can see that same number under the positive ground truth column. So, and the two numbers that are right below it, 5 and 10, add up to 15, which matches the 15 patients that we had with that particular disease, our positive patients. So in total, the population we're looking at is 15 patients with that disease. And how many of these patients did our model detect? And that would be our true positives. Because what true positives mean, this first cell in our table is cases where the patient was positive and our model detected those cases. And we have 5 of those. And so the numerator is going to be 5. 5 divided by 15, which is going to be 0.33 or 33%. So this is our recall. All right, let's put this in and express this in terms of an equation using the 4 quantities in the confusion matrix. So we can say recall is, well, the denominator is all positive cases, and if you look under P in the ground truth, you have true positives plus false negatives. So this is all positive cases in your data set. All your positive cases are either true positives, which means cases that were positive in reality and you detected those, or they could be false negatives, which means, again, in reality, these are cases that were positive, but your model mistakenly predicted those as being negative, but in reality these are positive. So these two quantities, true positives plus false negatives, together these two numbers should add up to the number of positive cases, confirmed positive cases in your database. So that's the denominator. The numerator, number of correctly detected positive cases. And that's going to be a single number, your first cell in your confusion matrix, the TP, true positive. And so this is going to be true positives over true positives plus false negatives. And so, and again, it's good if you can remember these simple equations based on the confusion matrix, but I think what's more important is to have an intuitive understanding of these concepts. And so let's focus on recall a little bit, and I want to ask the same question. Is it enough just to report the recall for a model, or what's the issue with just reporting the recall? So recall gave us a little bit of more information, so now we know the accuracy of the model is 75%, we know the recall of the model is 33%, but why is this not enough? So if you think about it, my model can play another trick. So in recall, the focus was on positive cases. And the question we answered was how many of those positive cases did our model detect? Now, one thing our model can do is our model can predict every single patient as positive. It's a different trick that my model is playing. It's not a good model, it's only playing tricks. So in the case of accuracy, because most of my labels were negative, my model decided to predict everything as negative and managed to get a high accuracy score. And that might fool us because we think we have a model with high accuracy, where in fact the model is not a good model. Now in the case of recall, our model is doing the opposite of that. Our model is predicting every record, every patient to be positive, And by doing that, of course, because everyone is predicted to be positive, you will get 100% of the positive cases. So if you predict all those 100 patients to have the disease, well, the 15 patients that actually have the disease are going to be among your positive predictions. And so you could say, I have a model with 100% recall. In reality, we know this is not a good model, even though it managed to score a really high number in terms of recall. And so we need to complement the recall with yet another metric. And we call that metric precision. So what precision means is that your model is looking at every single record and it's making a prediction, positive or negative. Now, if you look at the set of all positive predictions by your model, every time your model says, here is a patient with a positive prediction, so your model is making a positive prediction. If you look at that population that are predicted to have the disease, what percentage of that population actually has the disease? So what percentage of your positive predictions are actually positive? And so if we wanted to write this down in words, precision would be, in the denominator, it would be all positive predictions. So these are all positive predictions by your model, but we don't know if these positive predictions are good predictions or bad predictions. It's just positive predictions. And so in the numerator, we're going to say number of correct positive predictions. Number of correct positive predictions. And so in numbers, if we wanted to put in numbers, so I could say my precision is, if we go back to our data set, how many positive predictions did our model make? So let's put this in numbers. In our example, the denominator is going to be total number of positive predictions. So if you look at our confusion matrix, if you look at the row with positive predictions, there's two numbers, 5 and 15. So this is the total number of cases where we had a positive prediction. So our model looked at 100 patients and basically said 20 of these 100 patients I predict to have the disease. So 5 plus 15, this is going to be 20. Okay, what percentage or how many of these 20 were actually positive cases when compared to the ground truth labels? And as you can see, we have the true positive cell here, which basically says, yes, you made 20 positive predictions, but only 5 of those positive predictions were good. The other 15 are in the false positive cell, which means you were wrong in predicting those 15 cases to be positive. And so the numerator is going to be 5. So this is 5 over 20, which basically means 25%. If we look at these numbers, now I have an accuracy of 75%. This is my accuracy. I have a recall of 33%, and I have a precision of 25%. And so these three numbers together is gonna give the users of your model or even to yourself a better understanding of the goodness of your model, how well your model is performing. So if you think about what would happen if you had that model that was predicting everyone to be positive, and that way it was managing to score high in terms of recall. If you look at the precision score for that same model, you have 100 positive predictions. Basically everyone was predicted to be positive, so the denominator in your precision equation would be 100. And if you look at the numerator, you have 15 patients with that disease. And so 15 over 100, you would have a model with 15% or 0.15 precision, which is a low, relatively low number. And so basically, when you look at both precision and recall, you can see that even though the model has a high recall, it has an extremely low precision, and so probably it's not a good model. And so there's an interesting relationship between precision and recall, and oftentimes when you try to increase one of these numbers, the other number decreases. And so the goal in building models is to, of course, try to push these numbers as high as you can. The higher the precision, the better. The higher the recall, the better. But because we know there is this relationship between precision and recall, where focusing on one number, pushing the other one down, you really want to get to a point where you have enough of precision and you have enough of recall to basically be able to call your model a good model for its intended business purposes. And one thing I want to emphasize here is that there is no set threshold. There is no such thing as 80% recall or precision is good or 90% recall or precision is good. Even though we say the larger these numbers become, the closer these numbers become to 1 or 100%, the better. But every use case, every problem is going to be different, and it's usually the problem, the scientific problem that you're solving or the business problem that you're solving that's going to dictate what would be an acceptable level of precision and recall and accuracy for your model. So let's, just for the sake of completeness, put our precision in terms of the 4 numbers in the confusion matrix. The denominator, of course, is going to be all positive cases, all positive predicted cases, which basically is going to be true positives plus false positives. So this is everything that was predicted to be positive, either correctly or incorrectly. And then the numerator is going to be true positives, just the ones that were true, just positive predictions that were true. Now, we use different metrics like accuracy, recall, and precision to capture the goodness of our model. But in a lot of the cases, especially if we are trying to automate the process of finding the best model, and we're going to talk a little bit about it in our future lectures, it's useful to be able to capture the goodness of a model in a single number. We're going to use another metric called the F1 metric. So the F1 metric is really a combination of recall and precision. So recall and precision together should give you a very good understanding of your model performance. But in some cases, we really need to combine these things together and come up with one number. In model fine-tuning, which is a topic that we're going to talk in the future, we build hundreds or thousands of models automatically, and the idea is to pick the model with the best performance. Well, the question then becomes, what's a good model? And so because we're trying to automate tasks, it's helpful to kind of capture the goodness of a model in one single number and kind of find the model which scores the highest in terms of that number. If you combine these things together, you come up with one number, then you simplify the problem. The problem simply becomes pick the model with the highest F1 score, for example. So the equation we're going to use to combine precision and recall, that equation is going to be 2 times precision times recall divided by precision plus recall. Now, why do we use this equation? So first of all, this is called the harmonic mean of precision and recall. It's a type of mean. So the question you might be asking is, well, why do we use this equation? Why not just combine precision and recall using arithmetic mean, the regular mean? I'll try to give you an intuitive answer to that question by showing you an example. Imagine you have a model and the recall for your model is 0.1 and the precision for your model is 0.9. Now, if you think about the arithmetic mean of this model, this is going to be 0.9 plus 0.1 divided by 2. I'm just computing regular mean. So the arithmetic mean of this recall and precision is going to be 0.5. So you could say that single number that I'm going to use to measure the goodness of my model is 50% or 0.5. But then let's look at another example. I have a different model, and my model has a recall of 0.4 and it has a precision of 0.6. Now again, if I compute the mean, this is going to be 0.4 plus 0.6 divided by 2, because I have two numbers. I'm computing the average of two numbers. And again, this is 1 over 2, which is 50%. And this is the problem. I have two models with very different behaviors. One model is very good at precision, really bad at recall, 90% precision, 10% recall. My other model is kind of average in terms of recall precision, 40% recall, 60% precision. But when I compute the arithmetic mean of these two numbers, I end up getting 0.5 or 50%, which is kind of, I'm losing information. Now, if I just told you, you have a model with an average performance of 0.5, I'm really not telling you much about my model. You're losing a lot of information. I'm really not capturing the concept of the amount of recall and precision in one single number. Now let's go back to our F1 score, which is the harmonic mean of precision and recall, and do the same computations and see what we get. So I'm gonna say F1 is, in my first example, 2 times precision, which is 0.1, times recall, which is 0.9, divided by the two numbers, the precision and recall. And my denominator is going to be 1, my numerator is going to be 0.18. I'm going to end up with 0.18 or 18%. Now, and as you can see, it's clearly very different from your arithmetic mean. Now let's do the same computation for the second example. So again, the equation is 2 times precision, which is 4 point, times recall, which is 0.6, divided by precision plus recall. And again, the denominator is going to be 1, and the numerator is going to be 0.48, so my number is 48%. Now look at these numbers, 18% and 48%. How nicely this is capturing the concept of the fact that my first model is kind of an extreme model. It's extremely good at one measure, really bad at, extremely bad at another measure. And so the overall performance of my model is 18%, which basically is telling me this is not a good model, probably. Whereas in the second case, my F1 score ended up being 48%, which is kind of telling me it's close to midpoint. It's an average model. It's performing average in terms of recall, and it's performing average in terms of precision. So I was able to capture that concept of precision and recall in a single number. And so this is what I'm going to use to automate the hyperparameter tuning of my model, which is a discussion for the future. But this is the measure I would use to capture the goodness of my model in one single number. It's very common for every and all model that you're going to build to report these 4 metrics: accuracy, precision, recall, and F1. And you have to make sure that you have a very good understanding of these 4 concepts. There are more advanced concepts for measuring the performance of a model, concepts like area under the curve or ROC graphs, but I think these 4 metrics are the basics, and you are expected to provide these 4 metrics for every single model that you build, and this is what you're going to use to fine-tune your model. So you're going to build a model, you're going to report these 4 numbers, look at these numbers and decide if your model needs further improvements, and then you go and change your model. We talked about model building being an iterative process. You have to iterate over your model building phase and make changes and adjust your models and then reevaluate your model. And you do this a number of times. And at some point, when you look at your metrics, you basically decide that your metrics are good enough for the business purposes or the business use case, and that's where you stop. Thanks for watching the video. I hope this was useful, and I'm looking forward to seeing you in our next lecture.